Dear students, welcome back. Let us think about properties of Fourier transform. The first property is the linearity property. The linearity property states that if x1 of t is Fourier transform is x1 of omega, or the Fourier transform of x1 of t is x1 of omega, and the Fourier transform of x2 of t is x2 of omega, then the Fourier transform of a into x1 of t plus b into x2 of t is given by a x1 of omega plus b x2 of omega, where a and b are constants. So here we can see the Fourier transform of x1 of t is x1 of omega. Similarly, Fourier transform of x2 of t is x2 of omega. Then a linear combination of these two signals, that means a x1 of t plus b x2 of t, its Fourier transform will be equal to a x1 of omega plus b into x2 of omega. Okay, so how can we prove it? Let us find the Fourier transform of a x1 of t plus b x2 of t. Now, as per the definition of Fourier transform, it will be equal to integral minus infinity to infinity a x1 of t plus b x2 of t into e power minus j omega t dt. So we all know about the uh, definition of Fourier transform. Let us see here in the bottom. This is the definition of the Fourier transform. That means if we have a signal x1 of t, then its Fourier transform is nothing but integral minus infinity to infinity x1 of t e power minus j omega t dt. Okay, that is defined as x1 of omega, or that is taken as x1 of omega. Okay, this is x1 of omega. So that is the Fourier transform of x1 of t. So by using the definition, we can put the Fourier transform of a x1 of t plus b x2 of t in this way. That means we have to multiply these two terms with e power minus j omega t dt. Okay, so now it becomes integral minus infinity to infinity a x1 of t into e power minus j omega t dt. We can see here we are multiplying this term, the first term, we are multiplying it with e into minus j omega t, e raised to minus j omega t dt, plus second term b x2 of t into e raised to minus j omega t. It means this is of the form what? A plus b into say x. So that will be equal to x plus bx. Okay, so if there is an integral outside, it will become integral ax integral bx, like that. Okay, so we all know about it. So here in the next step we can see, since a is a constant, the a has been taken outside, so it becomes a into integral x1 of t e raised to minus j omega t dt, b into integral b is a constant here, b is taken outside here, so b into integral minus infinity to x2 of t e raised to minus j omega t dt. So that is nothing but a into x1 of omega plus b into x2 of omega, because as per the definition of Fourier transform, this term integral x1 of t e raised to minus j omega t dt is nothing but x1 of omega. Similarly, integral x2 of t e raised to minus j omega t dt is x2 of omega. So we can see the Fourier transform of a into x1 of t plus b into x2 of t is nothing but a into x1 of omega plus b into x2 of omega. That means this x1 of omega, that is a capital X1 of omega, that is the Fourier transform of x1 of t. Similarly, capital X2 of omega എന്ന് പറഞ്ഞാൽ, that is the Fourier transform of x2 of t. Okay, so we can see here the Fourier transform of x1 of t is nothing but x1 of capital X1 of omega That means integral minus infinity to infinity x1 of t e raised to minus j omega t dt is capital X1 of omega. Okay. So capital X1 of omega. അതായത് x1 of t യുടെ Fourier transformനെ നമ്മൾ represent ചെയ്യുന്നത് capital X1 of omega എന്നാണ്. In some of the textbook it is put as a, you can see x1 of t യുടെ Fourier transform എന്ന് പറഞ്ഞാൽ ചില ടെക്സ്റ്റ് ബുക്കുകളിൽ x1 of capital omega എന്ന് കാണിക്കാറുണ്ട്. മറ്റു ചില ടെക്സ്റ്റ് ബുക്കുകളിൽ x1 of j omega എന്ന് കാണിക്കാറുണ്ട്. So these are simply some notations or indications of the Fourier transform. Different textbooks are not indicating or giving notations in different forms. That's all about. It's nothing but x1 of omega is nothing but the Fourier transform of x1 of t. You can represent it in this other ways also. Okay, so this is the first property, that is the linearity property. Thank you.